Hello, ladies and gentlemen. Today we're going to be talking about how to represent ionic and covalent bonds using Lewis structures. We learned how to do electron dot models last unit to represent the valence electrons. We've also learned that the valence electrons are what change or are modified to allow a bond to occur. Now, ionic compounds have the actual transfer of electrons. So these are pretty straightforward. We're going to be creating ionic dot models and simply writing them next to each other in the correct proportion. In this model, we see that the sodium has one valence electron to give, and the fluorine needs one more. In this case, sodium would form a +1 ion, and the fluorine would form the -1 ion when the electron transfers to it. Here we see that the sodium has the no dots showing that the electron was given up, and the fluorine shows all 8 dots around it to show that its outer energy level was filled. So these ones we're not going to be doing a lot of time with because they have more of those crystalline structures. Now, for covalent molecules, because instead of transferring electrons, we share them, we have to have a little bit different system for being able to represent that. So in this case, our dots still indicate the individual electrons, and the bars or lines represent a shared pair. So anytime you're counting electrons, we would always count the line as 2. So the steps you see listed here are the order in which we should determine how to draw out the valence electrons in the Lewis structure. Everything goes back to the total valence electrons coming in from the elements must match the drawing at the end. So if we take a look here, phosphorus has 5 valence electrons, and each individual fluorine has 7. So our total number of valence electrons in the diagram should be 26. So what we do initially is simply draw them out, and I'm just going to draw what that phosphorus looked like first. And then the lines connected with the single electron on each of the fluorines. So the easiest way to begin is make a single bond with any unpaired electrons between 2 of the atoms, and then we can go back and count how many total we have. If you are short electrons, where you don't have enough to go around, but you've drawn in every electron you can start with, the cons elements, as we see in the bottom, carbon, oxygen, nitrogen, and sulfur, can create double bonds and share more pairs. So let's count up how many electrons are in that diagram. So each of the fluorines has 8, including the 6 individual dots and the one line for 2. We have 3 of those, so 3 times 8 is 24, and then we see the additional 2 electrons on the top of phosphorus for 26. So the drawing is correctly representing the number of electrons we identified as needing in this particular set. The easiest way is to always start with the ones that you have. Start with the plain dot models of the original valence electrons and start making your single bonds in the unpaired electrons. So let's look at a couple examples. Here we see the Bohr models representing it, and we'll draw out the examples for these different compounds and molecules. What I'll now do is replace the 2 individual dots with a line to represent those 2 electrons. For hydrogen, with each one coming in, we have only one line and our 2 electrons represented. For the next one, we would have the fluorine, which would have 7 and 7. Again, a single unpaired electron on each side represents a place I can share that pair. When I look at the next example, I have an two oxygens and a carbon to make CO2. If you look at the Bohr model, we see there are two pairs of shared electrons going on here because we didn't have enough to go around. So in kind of a stretch, if you look at for some of the places I can make the pairs, that will show us where those happen. And then if I simply rearrange those, I can draw it out a little bit more evenly and I meet my criteria. Now for the last one, we take 7 electrons times 4 to 28 for the fluorine atoms, plus 4 from the carbon to be a total of 32. And if you take the connect the dots approach, as long as it doesn't look like there's dots on the end of your lines, you're good to go. So if we count that up, each fluorine has 6 individual electrons, plus the 2 represented by the bar, the line indicating a shared pair. And I only count that bar once, so I don't count it again when I go to carbon. So if I take my 8 for each fluorine and multiply it by the 4 fluorines that are attached, I would get my 32 electrons I was supposed to account for. Now, in some cases, we may break some of the rules that we've introduced for those steps that you wrote down to follow. Most cases, it's going to deal with breaking the octet rule. With some of our smaller elements, they can actually be stable without having that full set of 8. And the most common ones that deals with are beryllium and boron. Now, in the case of the BF3, when we count up, boron would be bringing in 3 electrons, and each fluorine brings in 7. So I know my total diagram is going to have 24 electrons. So if I start with the boron in the middle, and I do my connecting up where I have the unpaired electrons. At this point, if you would count the electrons around the boron, we would only see 6, 2 in each of the lines that are there. That would be breaking our octet rule. But boron, as we see here, is one of our examples where it's stable without it, which is important because it can't create double or triple bonds, and I only have 24 electrons in the diagram, so the correct amount is already represented. Now, if I take a look at the expanded octet, sometimes as we get larger elements, they can be stable with more than 8 electrons. Remember we said once you hit the 3rd energy level, we have that D sublevel that starts kind of making things a little bit interesting. So as long as you have an element in the 3rd energy level, this rule can apply. The big thing that's going to impact next is the 3-dimensional shape of the molecule because of these extra electrons. So the center atom is the one that can potentially have the extra electrons, never anything else. Let's take a look at the PCl5 and look at that example first. In this case, I'm going to have to place 40 electrons from the valence electrons there. So I'm going to start in my normal way. Now, in this case, if you notice, in order to be able to bond 5 chlorines to this, you have to have 10 electrons around the phosphorus. I have an extra pair of electrons attached to the phosphorus that are making it break the rule. But if you look, 5 times 8, each chlorine has 6 unpaired electrons and 2 in that shared pair. Now, let's take a look at a different one that doesn't automatically have extras from the bondings. Let's take a look at the ClF3. Now, in this case, I have all of the dots drawn. And the way I drew it out, we're going to be able to have to do some adjusting of our visuals on our pairs of electrons. But all of the valence electrons that came in from this are represented right now, so I know I have the right amount. So now I'm going to start pairing up. On the right, that Cl has 1 open position to bond. But on the other sides, notice that I have to bond with one that appears to be in a pair. So in this case, I made the connection to show the shared pair of electrons. The chlorine has 3 bonding pairs for 6 electrons plus 4 lone electrons. So that means there's a total of 10 around it. In this case, this is stable because chlorine is in the 3rd energy level. I put it in the middle because it's the less electronegative element. And I can consider those other electrons as 2 lone pairs. So they are lone electrons not being shared, but they are in pairs. So as long as your number of electrons coming in from the valence calculation is correct, that is the biggest thing you need to be looking for. If you see that you break the octet rule on that middle element, just confirm that it's either small like boron, or it meets the criteria of the 3rd energy level if you have more than 8. But every single drawing you have is going to have an even number of electrons because everything has to be paired. After you view the video in next class, we'll be taking a look at some practice examples for you to work and apply these skills.